Good afternoon to all respected members of the committee. Thank you for attending my thesis defense. My name is Aditya Chaudhary, and I'm here to show the results of my thesis on wind resource prediction with a multi-scale method based on RANS and mesoscale wind simulations. We know that wind power is one of the most cost-effective energy sources currently accessible, and more importantly, it has a low environmental effect, which means that it can play a big role for countries bound by the Paris Climate Agreement. Subsequently, the goal of this study is to overcome the technical challenges that prevent researchers from using precise methods of predicting wind energy influenced by complex terrains, mountains, for example. To identify high potential locations for installation of a wind farm within a target area, we implemented a multi-scale technique for wind resource assessment that allows us to combine the mesoscale wind forecast with the computational fluid dynamics or CFD model for turbulent flow simulations. The results show when these two independent approaches are combined, the spatial resolution of the wind forecast is improved. We have also put to test two different Reynolds averaged Navier-Stokes or RANS models, which are steady RANS and unsteady RANS, in dealing with the complex atmospheric boundary layers. A lack of information in existing literature regarding the transient solution with unsteady RANS model for similar application gives us a chance to study the results and then compare them with the results of steady RANS simulation. In theory, we expected similar results between the simulations, and indeed, the results show the same, even though some minor differences are appreciated. We will see why this is the case. The procedure of this simulation is based on the computations performed on open source platforms to simulate the wind at the mesoscale and local scale levels to make the simulation easily repeatable. The approach is tested on a location in the south of Italy, and the simulation results have been compared with the mesoscale wind data or measurements taken from the paper of Professor Castorini and others. The initial conditions of the atmosphere and the orography data in standard triangle language are passed on by an interface algorithm to the local scale domain as boundary conditions for the CFD solver. Since the planetary boundary layer is not pressure driven, turbulent kinetic energy K and the wind velocity U are projected on the boundaries of the local scale domain. Remaining variables are taken according to the CFD solver scheme related to the atmospheric boundary layer theory. A new study is conducted over an existing methodology where a 20 by 20 kilometer digital terrain model is taken from the Regional Cartography Institution, and it is converted to a standard triangle language following a procedure from the existing literature. The wind measurements provided by the mesoscale model is averaged over a time period of 15 minutes. This averaging method creates a snapshot of the wind's evolution over time leading to the forecast. Numerical weather prediction model makes this possible because it solves nonlinear equations of motion and continuity equations to represent the dynamics of the atmosphere. Next, a steady RANS simulation of this snapshot is done, which allows us to improve the spatial resolution of the wind prediction across the given time scale. The RANS model used is the standard K epsilon turbulence model, which is based on the formulation for a planetary boundary layer theory by Richards, Hargreaves, and others. Surface obstructions like buildings, trees, and others are parameterized as shown in the figure. Once the target area is defined, the local scale wind field prediction is expected to be affected by the orographic detail of the area, roughness length distribution, the space-time prediction of the wind at the mesoscale level, the turbulence modeling adopted for the local scale simulation, and the way the data is transferred from mesoscale to local scale. The prediction of wind field is done for a site located in correspondence to a weather observation station of the Basilicata region. We can view the 3D and 2D image of the site with the help of Google Earth. The mesoscale simulation data is taken from the reference source, and the time period for the test corresponds to 8 hours ranging from 10 and 18 Central European Time of December 11, 2019. The timescale is selected keeping in mind the differential heating experienced by the atmospheric boundary layer during the day. We selected the results at 17 CET for the study because a strong and regular wind is observed in the planetary boundary layer 10 meters above the ground. For CFD simulations, the interpolation of mesoscale solution on the grid is required because mesoscale has a much coarser resolution of 1.2 kilometers to 15 meters of the local scale. This is accomplished by post-processing the time-dependent mesoscale solution at the sample locations shown in the figure. The dashed line in the figure shows how the local scale computational domain is nested inside the mesoscale grid. The downscaling technique increases spatial resolution by covering a set of 4 by 4 by 11 grid points of mesoscale model into a collection of about 3.6 million grid points in the local scale, covering the same region. The CAD surface of the ground obtained from the digital terrain model is used to cut the domain and reproduce the ground patch. Then to construct the mesh, we use the tool SnapPX Mesh, which is an inbuilt 3D measure in OpenFOAM. We first created a structured mesh for in the Cartesian system. This base mesh defines a hexahedral domain bounding the area 6 by 6 kilometer, starting from the zero elevation to the height of 1.25 kilometers. A sequence of operations is done to create the mesh for a complex geometry with the SnapPX Mesh tool. The most relevant to the procedure is the refinement technique for the terrain. Global refinement level is used to control the surface refinement. All the volume and surface refinements are done in reference to the background or base mesh. At the end, a procedure of layer addition is performed to improve the refinement close to the ground. The base mesh has 81 points in X and Y directions and 41 points in the Z direction. The simulations are performed in unstructured mesh with 3.6 million hexahedral cells. These figures are for the visualization of the local scale computational grid. The left section is the top view of the domain covering 6 by 6 kilometer. Top right section is the Gaussian surface and bottom right section is the wireframe of mesh in west to east alignment. So we first perform a steady incompressible rand simulation in OpenFOAM environment to verify the downscaling methodology in the target area. 8,000 physical pseudo time steps of steady rand simulation are followed by unsteady rand simulation, which is in the end averaged over 2,000 physical time steps to conclude the simulation. The results are then compared one-to-one with the help of snapshots or forecasts for each case. The table lists the algorithms and basic control parameters used for the simulation. To converge to a steady-state solution, simple foam solver is run roughly for 6,000 pseudo time steps. At this point, the residuals for all the equations converge to 10 to the order of -6, as shown in the figure. For convergence to a transient solution, we ensure stability of the simulation by running for 7,000 physical time steps before averaging the last 2,000 time steps for making an accurate forecast. GNU Plotter is the tool used to plot this and monitor this information to avoid unnecessary inflation of computational cost. The analytical approach to study the results is based on the unsteady rand simulation performed over a large time scale of 9,000 physical time steps, which guarantees that the averages arrive to asymptotic convergence. We will look for differences between steady rands and unsteady rands for same average boundary conditions, and if major differences are observed, then we can conclude that steady rands is not useful for this kind of application, but as stated before, we expect similar results, and indeed that is the case. We verify the results with the average wind condition in the snapshot. We will now see some results of the simulation. To study the flow parameters predicted by the local scale model, we chose a single forecast or snapshot for the simulated day. Here we see the comparison of wind velocity fields, where the arrows are aligned parallel to the wind direction from the northwest direction. The differences are not straightforward, but later verified with the computation of wind power density at a high velocity point for both simulations. The rectangular boxes in this figure and the subsequent figures in the slide highlight the differences between steady rands and unsteady rand simulations. In this figure, the wind velocity vectors are visualized with two mutually perpendicular planes, slicing the domain and passing through the measurement station. This is done to observe any variation in the direction characterized by the orographic features of the terrain like peaks, valleys, or gorges, but the results always appear similar. Another observation is the fact that the wind situation is not uniform on vertical profile because of the stratification of the atmosphere and the convection, which demonstrate the realization of wind exposition. This is an animation where the stratification of the atmosphere can be observed with the variation of the wind direction of wind velocity streamlines along the planetary boundary layer height in the Z direction. So these are some stratification. Here we can see the comparison of turbulent kinetic energy fields on a horizontal slice of the domain compiled at 800 meters elevation. Slightly pronounced results are noticeable with the high color gradient in the case of unsteady rands in comparison to the steady rands. And it is later verified with the calculation of wind power density at one wind condition. For a better visualization of the turbulent kinetic energy field, the ground patch is used in this figure where the flow behavior is visible at several peaks of the mountain. To make the ground explicit, zero velocity is imposed on the faces or boundary sides of the ground, which ensures that no slip boundary condition is applied and expected behavior of the surface boundary layer can be experienced at the ground. The results are similar to the previous figure, though it is observed that the turbulent kinetic energy has been predicted better by unsteady RANS approach, especially in the near peaks region. As expected, a strong wind is blowing from the northwest direction and turbulence develops close to the mountain peaks. This plot is a quantitative comparison of vertical velocity profile. The analysis is done on the vertical plane or 2D slice orthogonal to the main wind. The peak wind velocity can be seen between the elevation of 750 to 800 meters, which indicates potential areas for wind farm installation. We also compared the flow separation at southwest direction parallel to the inflow for some peaks of the mountain and found an identical trend which verifies the similar nature of the simulations. This figure shows the wind direction results of downscaling the mesoscale prediction to the local scale wind direction at 800 meters elevation. The average wind direction is negative 54.4 degrees from west to east and negative 52.8 degrees from south to north. This information indicates the direction of the main wind which is required for the wind turbine orientation. Similar trend is seen for both steady RANs and steady RAN simulations. So considering the fact that the wind turbine will always work oriented with respect to the main wind, a sequence of slices is taken as shown in the figure. They are used to visualize the wind power density to locate the potential areas or the best possible area in the domain where a wind farm can be installed, marked with black rectangles here. We evaluated the wind high power density areas with the help of slice orthogonal to the x-axis and then focusing on the radius or vicinity for better visualization. 11 parallel slices are taken with a spacing of 1 kilometer each. Maximum wind power density is computed to be 2.9 kilowatt per meter squared on one of the peaks of the mountain, where the velocity is 16 meters per second. The numerical result from the computation of wind power density at high potential point is shown in the domain. This is done as a sample application because for a detailed wind resource assessment on the site, this procedure has to be applied for a range that covers all the wind directions, and the boundary conditions that come from the mesoscale model should be taken as an average from each direction taken over a large time scale, for example, over a year. So this is a sample application. The calculation at this point shows that the unsteady RAN simulation is just marginally better. With unsteady RAN simulation, we get 8.32 kilowatts per meter squared, whereas it is 2.818 kilowatts per meter squared with the steady RAN simulation, which is an improvement of just 0.005% or 14 watts per meter squared. This means that the fluctuations captured in the transient solution are not able to improve the results of RAN simulation considerably. So some conclusions of the study are when mesoscale and CFD approaches are merged, it is possible to improve the spatial resolution of the wind forecast across a time period of a few hours. The maximum velocity was expected at the peak of the mountain, but that is not the case in our result where there is an offset distance between the peak and the point of maximum velocity where we have the maximum power density. As a sample application, the power density is verified on a point at the height of 200 meters above the ground. The location of this high power density area is suitable for the installation of wind turbines that have height in the range of up to 200 meters. As expected, wind resource prediction by the steady RANs approach and the unsteady RANs approach is qualitative identical. We can appreciate some minor differences, but we can easily neglect them because they don't have significant impact. Therefore, it would be preferable to use the steady RANs for reduced computational cost. So I would like to thank my thesis advisor and co-advisor for the opportunity to work on this thesis and the committee for the patience and observation through the presentation. Thank you.
Okay, thank you very much. Yes, I know that you have a density of power more or less equal to 2 point something kilowatt per square meter.
Yes, Professor.
Yeah, my curiosity, what about the velocity? It's very high velocity, maybe.
Yeah, because we observe some locations in the field that can be like good areas to install the wind farm. So, but maybe
what about the 80 you measure the velocity, 100 meters or more.
The elevation where this velocity is found.
Yeah.
It's like 200 meters, like 200 meters of the ground, because the observation station is at 761 meters, which is 10 meters above the ground, between in the center of the domain. So in this case, for example, where we found 2.9 kilowatts per meter squared power density here, the elevation is, you can see from here, maybe I don't know.
but it's still about
It's
in the region.
714 meters.
Okay,
Yes.
okay, okay. Thank you very much.
Thank you, Professor.